Good afternoon, everyone. We are going to present you in the following 20 minutes some of the work we've been doing, and we are still doing, trying to couple two theories. First, the optimal transform theory, and the second one, the statistical theory of Copula, in order to build, I would say, a more intelligent scoring function in some domains such as cybersecurity. So we are from Thales Communication. So the presentation is gonna be maybe a bit more application driven. So hopefully it's gonna be quite complementary to what we've seen before. So the presentation is gonna be in three parts. In the first part, I'm going to describe the challenge that we are trying to tackle. Challenge which deals with the detection of cyber attacks. In the second part, I will leave the floor to Benoit. He will present you some of the properties of the Copula function, especially highlight how we can choose a good Copula function for scoring, and make a link from Copula theory to optimal transport theory. And then we are going to conclude essentially by illustrating the performance of the approach we built on a regular data set. So first, a few words about the context and the challenge that we are trying to tackle. I think all of you are familiar with the challenge of cyber attacks detection. Attacks are more and more complex, they are more and more organized, and they are more and more difficult to detect. What you have to know is that I would say from 80 to 90% of the systems we are using to detect attacks are based on expert rules. So it's basically rules which are linked to attack patterns. So of course it is very suitable to detect known attacks. I would say that it's the best approach to detect known attacks. It's easily understandable. That's something important in cybersecurity, because when you have an alert which is raised, the operator has to understand the alert in order to initiate some mitigation action. So understanding the alert is very important. And it is very easy to add new rules. Basically, you just have to write a new rules corresponding to a new pattern of attacks. So this is good, but this is absolutely not sufficient. Essentially because attackers are using very customized and very new attack patterns. So you won't be able to detect those patterns with expert rules. That's why a lot of people have been working in the recent year on anomaly-based approach. Basically what you want to do is to be able to detect without any a priori information on the types of attacks that you are interested in. You want to detect any abnormal behavior, and in an incremental fashion. So it has many advantages. Of course, it is suitable to detect unknown patterns, but it can be time consuming to update the model depending on the model you choose. Alerts, that's basically one of the biggest difficulty. That's why not a lot of systems have been used operationally. The system can raise alerts, as I said before, but if the operator cannot understand why the system is raising an alert, then it's no use. You won't use the raised alerts. And another drawbacks is that quite often, but I would say that it's general in unsupervised anomaly detection. It raises way too many false alerts. So basically, the operator lowers his trust on the system. So what we are trying to do, what we've been trying to do, is trying to overcome these difficulties and build an approach, an unsupervised anomaly detection approach, which will be better than the existing one. Some of the notation that we will use. So yeah, anomaly detection can be formalized as a classification problem, either supervised one or unsupervised one, where y would be a binary random variable which will be equal to 0 if the event is abnormal, and 1 instead. It's quite an even inverse notation, but it will is the following notation that will be presented by Benoit. So P0 is the a priori probability of attacks. Usually it's very, very low. Could be, yeah, it's very, very low. Depending on the system, it's beneath one of, I would say, 10,000 or something like that. Very, very low probability. And X represent the characteristics of the events that we are trying to analyze. So it's basically a network event that can be characterized by many variables, many indicators, protocols, number of bytes exchanged, etc. So it could be very high dimensional vector. So you are able to write the cumulative distribution function of X in this form, simple form. And using this notation, we can of course write classical scoring function defined as the probability that an event is an attack, probability that y equals 0 depending on x equal x. And using the bias rule, we have this probability. We can estimate this probability using the classical maximum a posteriori estimator. Very classical. But actually doing empirical estimation, especially on this joint density in very high dimension, could be very difficult. When you want to be able to estimate using kernel density estimation, for example, it is known that in very high dimension, you will suffer the curse of dimensionality. So basically what we did is to split the problem using Copula theory. So what we do is basically estimate for each marginal the density, and then group all the marginal density using a copula in order to reconstruct the joint density. And we will see that it's very efficient from the computational point of view, but also from a statistical point of view.
I will present you some property on copula. So copula theory was developed first of all by Fréchet in 51, and we have a very important theorem given by Sklar in 59 on the copula. So the Sklar theorem gives us an existence and an uniqueness of a function that represents all the dependence structure between a random two random variables, and the so-called Fréchet-Hövding bounds give us two bounds of these copula functions. First of all, I will present you the Monge condition about the copula. So in copula theory, this condition is called the two increasing properties. So if I for example, if I look this square and I want to compute the square, the area of A, I can use this these things and obtain the Monge properties. The second one is the Lipschitzian criterion on copula. If I want to have to bound this difference, it's possible by Eulerian criterion. So now I want to model the joint probability between the attack event and the different characteristic of a network packet. So if I use the first Fréchet bounds, I can have this bound on the conditional probability, and if I use the maximum a posteriori rule, I can see it's not possible to have an attack if the event is not a very rare event. So now I want to know if it's possible to have a lower bound on these probabilities. So I use the lower Tsai dependence ratio that's given by the limits at very infrequent event of the ratio between the joint probability on the first bisectrix and the probability. So using the two increasing properties, it's possible to have these inequalities, and it's possible to show that if the lower tail dependence ratio is more like an half, it's possible to use this application to detect attack. So. Yes. So I want to know what it's happened when I was in very infrequent event. So I will study the variation of this function in the 0 to p0 interval. So when I compute the derivative, I obtain this function, and it's possible to see this function with 2 points of view. The first one, it's just a link with convexity if the function is two-time differentiable, and the second one, it's a link with Fisher informations. So here we introduce the link with optimal transport theory using a very used criterion in statistics, in classification problem. This criterion is called area under rock curve, the IUC criterion. So this criterion remains to make the best compromise between the detection rate and the false positive rate. So I want to detect all the attack, but I want to make any error. So it's possible to write the true positive rate and the false positive rate according to a Copula function, and to compute and to rewrite the IUC using the same Copula function. So if I just use a bivariate random vector, if for example in our case the network packet is only a bivariate one, it's possible to rewrite the area under curve as this expression, and here we have an integral we want to minimize. So for the optimal transport problem, we want to minimize a double integral under this constraint, and thanks to a previous work, we show we show that the solution is given by this equation in a density point of view, and the cumulative distribution associated to this solution is given by this one. And we will use this function in our context to detect anomalies.
Okay, so a few words about how the principle of the algorithm. I already talked a bit about that in the introduction. So we have an event at an incoming event which can be characterized by up to, I would say, a few hundreds variables. Here is a very simplified view. You have the source IP, destination IP, protocol. You have the size of the event, size of the packet. You have the duration, and you have something that can characterize the nature of the event, eventually the service or something like that. From that, what you want to be able to achieve is essentially estimate the probability or the density of this event, basically. And you want to be able to compare then the probability to a given threshold. Depending on the use case, it could be eventually a predefined threshold or a calculated one. So what do we do here is basically, as I told you, we take at the input the 6 variable in this case. We perform density estimation in an incremental fashion. I will insist on incremental fashion because in cybersecurity you want your model to be evolving, to be up to date. So you have to be fully incremental. So first, incremental density estimation, where we get all the marginal densities, and then The copula, as Benoit described, is basically a function which takes as an input all this marginal density and calculate the joint density. Actually, there are many ways, many copula families. As Benoit told you, we used the copula that he presented in a slide before. We have the joint density, and then we want to compare it to a threshold, 2 modes or 3 modes maybe. This one is in automatic mode. One thing you can do is basically define quantile. So basically you want to be able to get all the events that have, or the first % event that have the highest probability. So you can perform incremental quantile regression, and it will output a threshold, so you will be able to compare, or we also use extreme value models to do that. And at the output, we have the score for the event and the fact, and we know if it's considered to be abnormal or not by the models. So going to the experimental results. So we used actually one of the well-known used dataset in cybersecurity from the DARPA, and what we wanted to do basically is to compare the copula that we built with other well-known copula, which are Clayton copula and Fréchet's upper-bound copula. What will be interesting, I didn't mention it before, what we are interested in is not to have, I would say, the best detection rate. The most discriminative criteria would be the false alarm rates. Of course, it's always I would say it's linked. But for operators, what is the most important is the false alarm rate. So you want to be able to have the best detection, but given a false alarm rate which should be under 5%, for example. That's something we want to achieve. So what we did here is basically compare the performance of those 3 copula at a different quantile level on the density of the events. And what we can see from that is that basically, apart from the first quantile threshold here, we can see that for all the other threshold, the copula that works the best is basically the optimal transport copula. So we presented result here in cybersecurity, but we benchmarked that also in other domains, and this is quite consistent actually. So from an empirical point of view, it's quite always the case, but it's not yet theoretically proof, I would say. And I think that would be the last slide. So thank you for your attention. If you have any question, we'll be glad to answer. Thank you.